Binary subarrays with sum. Essentially, what it is what the problem wants us to find is we need to find subarrays which basically add to a particular value which is called goal here. So this is very similar to a problem called subarray sum equal to k, which is a very standard problem. Obviously, they have defined what a subarray is here. Subarray is a contiguous part of an array. But this is very similar to, as I was saying, this is very similar to subarray sums equal to k. And one thing I would say about this problem is this is a deceptively hard problem to solve. It looks it actually is slightly more difficult than it seems to be. So I'll tell you what I tried initially. So there is one approach which is the prefix sum approach which you can try. So essentially it's an array, right? Let me take another color of pen. So essentially this is an array, and then suppose we have all the prefix sums, right? So suppose we want to find what this contiguous subarray wants to sum to, then we can just take this prefix sum and then subtract this prefix sum from the entire prefix sum. We can take this prefix sum, right, and then subtract this prefix sum from it, and then we'll have the thing that we want. So prefix sum is one approach, but when I tried prefix sum, it was giving a TLE, and it was passing 60 out of 61 cases, and then for the last case it could not pass it in time. It was giving a TLT. It was heartbreaking. So this is one of the approaches which can be used to solve the problem, but it is not fast enough. There is another approach called subarray sum equal to k. So what happens in subarray sum equal to k problem? We maintain a map, right, which contains a particular prefix sum value, okay, and then it points to the index at which we find that prefix sum. How is it useful is, suppose we want to find we have a certain prefix sum y, and our goal is x. So if we find y minus x prefix sum in this map, that means uh, that uh, that means there can be suppose okay, suppose this was having till here the prefix sum value was y, not index but prefix sum value, and then we found that there is a y minus x prefix sum value here which we can find through a map. As we calculate the prefix sum, we also populate the map. Then that means we have this prefix sum, we have this subarray sum x, right, here, because y minus x would be x. That means we have our goal as a subarray sum, uh, seeing this. But the problem is, as I told you, this map stores the index at which the prefix sum is getting calculated. So this will be I, and this I has to be less than this index of this y. Suppose yi, this I has to be less than yi. That then only this sort of schematic can be practical physically. So this has to be valid. But the problem is the array given in this scenario is very very large, and this map gets very huge, and that basically goes out of memory. So if you use the same approach which is used to solve the subarray sum equal to k problem, subarray sum equal to play, you will find MLE, that is memory limit exceeded. So that's another heartbreak. So far we have two heartbreaks, right? Now let us look at how do we solve this problem. So we can't use the subarray equal to sum k approach, we can't use the prefix approach. So the way to solve this problem is kind of using the prefix sum, uh, but while calculating the prefix sum only we'll try to solve this problem. Uh, so how what is the basic empirical relationship for a prefix sum? So prefix sum of I would be just nums of I, right, nums of I plus prefix sum of I minus 1. So basically what I'm trying to say, what you can observe here is, in order to find the prefix sum of an I, we only need to know the previous prefix sum, and then we don't need any other information. So if you're keeping the entire prefix sum array into memory, that can be too much memory than what is required to compute the current prefix sum at least, right? And then our Objective in this problem is not to calculate the prefix sum, but in order to, but prefix sum calculation is important because we will not use the exact method of subarray equal to sum, but we will use some other method to solve this problem, a similar method. For that we need to make one other observation. So this if you can see, if you look at the problem, the value numbers in this problem is only 0 and 1, 0 and 1, 0 and 1, means there are no negative numbers. That means the prefix sum would always be increasing, right? Either will be same or will be increasing. So how we can use that is, so for example, we have values in the vicinity of a particular check, index check. I'll come to what it is, but these are the values, right? So we'll have some prefix sum here, and then one prefix sum here would again increase at this particular index. Let's say it's x, right? And then here it will also be x, here it will also be x, and then suppose here we'll have a suppose here also prefix sum will be x, right? And our goal is to get a prefix sum of 0, right? So that and then how do you do that? We'll take x minus goal, prefix sum at this point minus goal. This is the index into consideration, index considered, right? And then x minus 0, and then we'll try to find whether this prefix sum is there or not, right? Ideally we are trying to find the indexes and see whether the indexes are in the particular range, right? Indexes in range. But actually what we're trying to find is the number of indexes for this which is possible, or the number of indexes which are valid indexes, right? So again observe here we have x at this point, until here probably we'll have only x 3 times, right? X will be, if we only, instead of storing the indexes, if we only store how many times this prefix sum occurs, it will be 3. So basically this at this point, at this point, at this point we have x values, right? So if our goal is 0, what we want is, we can have this subarray, right? Which has which are basically, this is the subarray that we want, and this is another subarray that we can want, right? Because our goal is 0, right? So because we'll be so because, and then you can see that this value is 3. So if we basically take this value, we'll get the number of servers that we need. So what this store is number of indexes, number. So this I index is also less than this index, right? IC index, and this I index for this also will be less than IC index, and this I index for this also will be less than IC index. Instead of storing, so this will be probably I plus 1 and I plus 2. So instead of storing against x I plus I plus 1 and I plus 2, I plus 1 and I plus 2, I just store 3 instead, which is much more memory efficient, right? Right, that means at this point also the value is x, at this point also the value is x, at this point also the value is x, right? So and then that means that for this, when I say that at this point the value is x, that means this is a valid subarray. When I say that at this point the value is also x, this is another valid subarray. At this point the value is x, this is another. So we get 3 subarrays, which basically equal to the number of values which add up to which have that prefix sum uh, till that point, right? So so this prefix sum is not put into the map. Before that only all these calculations take place. So this seems to be valid, right? Because before putting this into the map, we already have the map having 3 as the number of times this particular prefix sum has occurred before this index, before the IC index. So this can sound to be very complex, and this is slightly complex. I mean, understanding subarray sum equal to k, it's also complex how that works, as I explained you I think here how the subarray sum works, and then how we can take the similar concept and then save memory of, instead of storing the indexes, just storing the value of how many times this has occurred. Works here is as I explained to you now, is also is very difficult to get in the first instance. But if you think about it and probably watch this video uh, maybe one or two times more, I think you will be able to understand what I'm trying to put across. So after all that explanation, let us look into the code. We're trying to do the same thing. We basically, again, this is for ease of development. We store the nums array size somewhere, and then we update a map which basically will map to the prefix sum to number of time that prefix sum has already occurred. This is the old prefix. Obviously, this old prefix is populated into the map. That means this has happened once, which is true. Count is the number of times we are having the subarrays attend to the goal. That is the one, that is the result that we want. Okay, and if the old prefix is equal to goal, the first variable itself is equal to goal, then obviously you have to increase the count to 1. Then a new prefix, right? This is just initializing it. So we have the old prefix, and obviously, as I explained in this empirical relation, this old prefix is sufficient to calculate the new prefix. So that is what is happening here. And then obviously new prefix equal to goal. So uh, that means if the prefix sum from 0 itself is equal to goal, obviously this is a valid subarray, right? So that is what is being captured here at this point. And then obviously that subarray sum equal to say concept. If we find a prefix sum, current prefix sum minus goal, then we basically count the number of times that prefix sum has happened. This I've explained in a lot of detail in the whiteboard. And then obviously now, if this is a simple job, we want to put this prefix sum into the array. So if it is or into the map, sorry, if it is not there in the map, we put the prefix sum as 1. Is the first time we have found it. And if it is already there in the map, we'll increment the value, and then we'll replace the new old prefix with the new prefix in the at the end, so that at the beginning of the next loop the new prefix can be calculated from this, right? So because the new prefix now becomes the old prefix for the next loop. So this is the code. This is a very deceptively hard problem to solve, and even the solution is put forward before you to understand that. I agree, but I hope I was able to do justice and I tried my best to explain you this problem. I see you in the next video. Thank you.